Hello everyone, it's a great honor to be here to introduce our work in IEEE Labs 2021. I'm Yang, a research fellow from Beihang University. My topic today is signal space separation for spin exchange relaxation-free magnetometer. This presentation is divided into three parts. I want to begin with subject selecting background, and then I'll move on to our experiment. Next, we are talking about our method, and finally, we'll land on our conclusion. Let me begin by giving you some background information about this work. In the past, some common structure brain diseases could be detected by MRI and CT. However, some neurodegenerative diseases have no difference in brain structure with normal people. MEG is a non-invasive technique to explore human brain activity by recording magnetic field, which generated by neural activities. And now, surf magnetometer has played a certain role in the monitoring of brain function signal, such as earlier diagnosis of AD, ADS, epilepsy, and etc. However, the signal collected by surf magnetometer is easy to be contaminated by various artifacts, such as power line artifact, cardiomagnetic artifact, air movement artifact, shaking artifact, and so on. These artifacts are usually several orders of magnitude larger than the brain magnetic signal, and they need to be filtered by certain pre-processing methods. And then I'd like to move on to the second part of the presentation. In this study, we propose a special noise reduction method for surf magnetometers. It is based on the traditional signal space separation method. Signal space separation is an advanced algorithm that can filter the signal in space. Signal space separation can divide the signal collected by magnetic measurement sensor into the internal signal from the sensor and the external signal. The internal signal is generated by the signal source close to the sensor origin place, and the external signal is generated by the signal source far away from the sensor. In this paper, we use the simulation method to set two dipoles with different spatial positions, one inside the sensor array and the other in the distance. Two dipoles send different signals. S is used to filter the simulation signal, and variance between the filtered signal and the internal dipole signal, which is calculated as a cost function to optimize the S parameters. In addition, we use the T1 MRI of the ICBM 2009 templated for the brain templated, and use the free surfer to reconstruct the structure of the brain, and use the MNE Python software to reconstruct the surface source space, and carry out forward modeling. This paper also uses ThinkNet Pro software to scan participants wearing helmets and HPI coins. And then the position of the HPI coin will be used to register the helmet with the MRI. In this paper, 26 channels array of Q-spin magnetometer was used, and a healthy 26-year-old participant to conduct auditory evoked magnetic field experiment. In order to simulate the auditory cortex of the participant, we use a sound card to play high-frequency or low-frequency tones at certain intervals. The pulse duration of both tones is set to 100 milliseconds and appeared randomly at approximately. We use the optimized SSS to filter the auditory signal. It is found that the induced response of the signal is more obvious after spatial noise reduction. The vibration of the signal is basically eliminated. The signal-to-noise ratio of the signal is improved. We drew the field map of the evoked response signal and found that there was an opposite position of the magnetic field on the right side of the brain. After using rap music to locate, we found that the dipole could be located in the auditory cortex. We also used S-laureate, E-laureate, and DSPM to calculate the inverse problem respectively. It can be seen that the source position after spatial filtering also be well positioned in Boltzmann zone 14.1 and 14.2. That concludes my presentation. In this paper, we developed a spatial noise reduction algorithm for surf magnetometers, which can optimize the optimal IEEE parameters for different surf magnetometers, so as to reduce the spatial noise of data. If anyone has any questions, please send me an email. That's all from me. Thanks for your attention.